be a confusion is what do we know? What do we have to know about redox as far as predicting products versus balancing? Do you feel like that's an accurate assessment of your unsureties for the test? That's a new word I just made up. Okay, uncertainties is the word I was trying to say. I was like, there's a word for that. All right, so predicting, you will either predict the products or you will balance it. You will not be asked to predict and balance a reaction for points on your test, okay? So we'll do one or the other. Everybody's on board with that concept?
Yes.
Okay, does that make sense? Is that clear?
Yes.
So then let's say if you were to predict a product, that would be, I just told you what compounds are in the reaction and your job is to figure out what they are. So that, do you want me to do one like that?
Yes.
Yeah? So let's say we were to react, I'm making this up, potassium chromate solution reacts with hydrochloric acid. Okay, so because we all know that this is a redox reaction, I'm not going to work at making it flowery, but I have faith in you that you can kind of put that together. Okay, so we know it's redox. The clue here, let's say dichromate. That's what we went over in class. Do dichromate. Hello, 6-hour people.
Are you videotaping?
I am videotaping this, so it's weird and creepy. Because 6-hour wanted to know what questions you guys had, and then I'll videotape 6-hour, and they can see what questions you guys have.
Hi, 6-hour.
Got it.
All right, so yeah, hi 6-hour. Everybody's saying hi. Okay. That was enthusiastic. So what are we gonna do first in this reaction? Yeah, that sounds like a great plan. So if it's potassium dichromate, that would be CR2. Yeah, sorry. K2CR2O7. You will not be told what dichromate is on the test. You have to know your polyatomic ions. I'm not telling you those. Definitely dichromate, permanganate. You want to for sure know what those are because I will not tell you those and I expect you to know what they become. And then it's going to react with hydrochloric acid, HCl. The main acids you would have to know and recognize would be hydrochloric acid, HCl, nitric acid, HNO3. I mean, those are the ones we're going to use the most. Sulfuric acid, H2SO4. I think those would be like the 3 acids we're probably going to come across. Hydrochloric acid, sulfuric acid, and nitric acid. Sulfuric is H2SO4. Nitric is HNO3. We're going to use these often because they're good at reducing your ions, like we talked about with nitric acid there. So here, in this instance, hydrochloric acid being our other one, let's talk about that guy. So what would you guys do next? Okay, so if we want to predict our products, this looks awful like just a double replacement reaction. So I know there's still a lot of people that are wanting to just switch my products and make KCl and H2CR2O7. But that's not what we're doing this time. And we know that that's not what we're doing this time at this moment, mostly because I've told you this is a redox problem. Okay, but it also has dichromate in it, so that's a pretty good chance. It's reacting with an acid, so you know your solution is acidic. I would say if this were a test, I probably would have thrown in a different word in there, like concentrated hydrochloric acid or acidified potassium dichromate reacts with hydrochloric acid, something like that. Try to throw in an extra word to give you a hint that it was not just a double replacement reaction. Fair enough? All right, so before we go to predict the products, we probably want to think about what ions are most likely involved. And so the best thing to do here is to separate my 2 reactants into my aqueous compounds. How do I know that these are both aqueous? Okay, so it's a solution and it's an acid. That automatically makes it aqueous. This also is an alkali metal, which would have made it aqueous. And while hydrogen isn't an alkali metal, it's still in that group 1. So we kind of use that as part of its rule to remember that it is always aqueous. Okay, so then we're gonna hunt through my ions. I've got 4 possibilities. I wanna see if there's any of them that right now I know that's definitely gonna do this.
The CR becomes CR3.
Awesome, I know this is gonna do something. And what it's gonna do is CR207 minus, or minus 2, excuse me, always becomes CR plus 3 for our current purposes. There's nothing, I've limited you to just a handful of things you have to have memorized. That's one of them. So you know that's going to become CR plus 3. What's going to happen to those oxygens? So they're going to partner up with the H pluses and become water. So that's going to take care of some of my H's, not all of them, but some of them. And so my CR plus 3. So let's think about what's happening for my chromium to determine if I'm looking for something that's being oxidized or something that's being reduced. So here, CR207, what's the oxidation state for chromium? +6 is correct. If you're not sure, because we were a little hesitant, we know oxygen's got to be a -2. There's 7 oxygens, so that gives me on that side a -14. To keep my overall -2 charge, chromium together has to be a +2. I'm sorry, +12. And since there's 2 of them, they each have to be +6 in order to get to +12. That's how I would do those oxidation states. You'll definitely have questions on your test. That's just what's the oxidation state. Hopefully that will be a good one for you to get. All right, so if I go from +6 to +3, have I gained or lost electrons? Gained. And so that means I have reduced. And so remember, when you gain electrons, you reduce your charge. It went from +6 down to +3. So if you're in your test and you're struggling, can't remember what's happening, look at what's happening to your charges. +6 reduces to +3. So then we've gained some electrons. So I know I'm looking for something that can be oxidized. So if you're going to be oxidizing, we're looking to lose electrons. Potassium's already lost 1 electron. Is it likely to lose any more? No, it's probably not going to be that guy. Hydrogen's already doing some stuff, plus it's also positive, so it's unlikely to be there. So my chlorine's probably going to do something. And that's the other one of the other things you had to have memorized was your chlorine. What's chlorine most likely to become, or all of our halogens become their diatomic state. So we went from -1, which is its oxidation state, because that's what its charge is right there, to diatomic chlorine, which is 0. Remember, it doesn't have a charge up there, so it has to have no charge overall. So if I go from -1 to 0, is that oxidation? Yes. Yes, it is. So here I've got an oxidation. And on that practice redox reaction, I labeled them as oxidation and reduction, so you could kind of see what was happening. That wasn't required on your test, but it would be, or your test, your homework. But it would be a good question to ask, like, for a test, you know? And honestly, then that's it. That's all I need you to do for this unit. When we pick back up on redox reaction later in the game, you can take this a little bit further. But for right now, I just want you to try to wrap your mind around this concept. So far, so good? Questions do you have about that? Right, because I don't have potassium in there. Yeah, that's a good question. Either you want to cancel it out from your, just like I did here, write it as your reactant and then write your full equation without it in there, or just go ahead and put it on this side and say, I know my potassium's not doing anything. But if I had asked you for the net ionic equation, I would have wanted you to draw it without that. And that's the most likely question for me to say. And so when you go to rewrite it, I'd probably suggest you write it like this.
I mean, also, if, like, not as like a different acid, like say like hydrosulf or sulfuric acid, would then would like potassium be oxide?
No, sulfuric acid would be, but that's not one of the ones that I've had you memorize, so that's not one I test you on this test. But later in the game, that'll be one you have to have memorized. And if you're just curious, it's on your stuff you should know but don't know sheet. That one's on there. Potassium is not ever going to be oxidized because in order to lose another electron, it would be moving it from its core electrons, you know. Taking an electron from a core electron is not likely to happen. So potassium would never be oxidized in a reaction. it'll always be a spectator in a situation like this. The reason we have to have potassium is because we can't get dichromate into solution without a metal there connected to it. Like we talked about in our FRQ most recently, you can't make a solution of just dichromate. In order to make a solution that has dichromate in it, you need to use probably an alkali metal, sodium dichromate or something like that. I can do another practice one like this and give you some examples of the other things that you have to memorize, or I can just remind you what those things are that you need to have memorized.
Just like a clarification, you said that we don't have to balance it, but like when the ions were being like, reduced and oxidized and everything, and like from chromate, the dichromate, it was like a 3 electron. So
You're talking about the fact that it was
Right.
CR207?
yeah. So then since that since it gained 3 electrons, then the other one only oxidized 1. So would you want us to multiply that 1 by 3 and then balance it? No, is that what you're talking about?
Yeah, I would say I wouldn't make you do that this test because you also have 2 chromiums here and only 1 chromium here. So I wouldn't make you do anything beyond what I said here. Okay. And so it would just be to the point of this is what the products are. Now I would look at how many electrons and how many balancing, and we'll pick that part up later in the game. Okay. So, and the same thing with chlorine minus. It went from Cl to Cl2, and you don't have to worry about that right now.
When would we be balancing the reactions?
Can you say that one more time?
When would we be balancing the reactions?
For this test?
Yeah.
Okay. Let me say this real quick. And then. Okay, so I think these are all the ones that I suggested you to know. So the fact that hydrogen peroxide can either become O2 or H+. Hydrogen peroxide can become water. So one of those is oxidation, one of those is reduction. It just depends on what is pertinent to that. This is also one of the first pages of your slide notes we took a few days ago. MnO4 becomes Mn+2, Cr2O7 becomes Cr+3, and Cl- becomes Cl2. Those would be the ones that I would recommend you having memorized in regards to a predicting the products type situation.
What is the charge of H2O2? Is there one?
H2O2 does not have a charge. And that, remember, is hydrogen peroxide. So this is the one instance where O2's oxidation state is a -1. Or whatever that's worth. Just anytime it's a peroxide.
Well, H2O should be by itself, or will it be with potassium?
So it could be in a question like this. Potassium dichromate solution is mixed with hydrogen peroxide.
Oh,
It would be partnered like that. It's not, hydrogen peroxide itself is not a polyatomic ion. Is that what you're asking?
So if it's mixed, it either becomes water or oxygen and hydrogen, or one of the other of the oxygen and hydrogen. But that's
So hydrogen peroxide is either going to become this on the product side, or it's going to become this
Okay.
for this test. I would want you to know it can do this or it can do that. So you'll have to look to see what's it reacting with, and then does it make sense for hydrogen peroxide to be oxidized or reduced in that instance?
so
And then depending on which one it is, you would pick that product.
which one is the one that if it's reduced?
Okay, so right here, oxygen's a -1 charge. Over here, oxygen, because we just talked about peroxide, that's what it is. So oxygen here has what's oxidation state? And here it has -2. So in order to go from -1 to 0, did we gain or lose electrons? Okay, we definitely lost because electrons are negative. So in order to be less negative, we had to get rid of them. So that's the oxidation one. So hopefully this is our reduction one. If we go from -1 to -2, is that reduction? Yes, because we became more negative. So that's reduction. Other questions? Okay, need to find a practice oxidation state balancing one real quick, and I will do that one with you. I'm gonna turn this off because it's making this weird. Is there one off the sheet you guys would particularly like to see? the balancing redox. Oh, I forgot. That's not what we're doing. That was fun. So this was the oxidation state balancing worksheet that we did early on. It's called Balancing Redox Reactions Oxidation State Method. And there's a handful of questions overall, and it's like got a big space and it says final equation. This one is, I guess I could show you guys on the board. Shouldn't have marked it up. Number 5. This one is number 5. Is this one an okay one to do? I just sort of picked one that I didn't think we had gone over together in class yet. Okay, so when we're doing our oxidation state methods, I'm going to talk through some of the important parts. The very first step, so notice this is a reaction I just have written for you. So your job is to balance it. This question would be pretty explicit, like balance the equation above, you know, something crazy like that. So you wouldn't have to add anything to it at this point in the game. You just need to balance what it says. So the first thing you want to figure out is what their oxidation states are. So let's start with that. You know that this is a redox reaction because your compounds are creating new things. It's not like they're just squishing together or breaking apart or anything like that. So you, if I didn't happen to identify it for you, chances are if I were going to have you balance an equation, I would have it be a redox reaction, if that's all we're doing with it. And if we're doing more with it, you'd probably know more information. So the first thing we're going to go through is balance or predict our oxidation states. So what's the oxidation state here for oxygen?
-2.
-2. Since there's 2 of them, sulfur state must be. And here, let's do oxygen. -2. And so there's 2 of those. Hydrogen's most likely to be what? +1. So I've got, oops, got a -4 here, a +1 here. So that's got to be +3. Does that make sense? Is that everybody comfortable with what I just did there? Okay. So then we're good with all those. How about oxygen here? And I have 4 of them, so that gives me -8 on that side. You can either just go ahead and say, you know what sulfur is, or sulfate is, or we can keep going. Hydrogen's +1, because we did that a minute ago. And in order to get these to 0, sulfur needs to be what? And how did I know I was going to 0 there? Because there's no charge on my overall compound. Okay, there's no charge on my overall compound. Some of you, and I'm fine with it, doesn't matter, are pulling the sulfate out and saying, I know sulfate has a -2 charge, because sometimes it gets a little bit confusing, especially if you have a lot. And I think this is a great way to do it, but just you can't do it both ways. If you separate sulfate out and you look at the fact that it has a -2 charge, then you have to ignore hydrogen and just figure out what's going on here. And it would still be +6 because this is still -2 and you've got an overall -8. So that would still be +6. So you get the same answer. It's just either separate it and give it a charge or leave it in the compound and it doesn't have a charge. Do you see the difference between those two? Okay, carrying on. So what would be oxygen's oxidation state here? And how about nitrogen? So which one's changed? Sulfur, and you said nitrogen. Okay. So good things. First thing is we had 2 things changing. That's always a good sign. How about for my sulfur? It went from +4 to +6. Did that mean it gained or lost electrons? It lost electrons. It became further away from being balanced. So it was oxidized by how much? 2 electrons. All right. So then we're going to do nitrogen. Nitrogen went from a +3 to a +2. So what did it do? It reduced. It reduced by how many electrons? 1 electron. All right, so first thing we need to do before we tackle our electrons balanced, which obviously they're not, is make sure our sulfur and our nitrogen are balanced. Because if they're not, then you would need to adjust your electrons a little bit. In this instance, they both happen to be balanced, so it worked out great. But if for whatever reason there'd be like an additional nitrogen here, then you would have had to say you need 2 nitrogens here, and you would double your electrons. So you want to address that situation first, but it doesn't happen all that often, so it's kind of hard to give you examples. So then if we keep going, my electrons do not balance, so what do I need to do to get them balanced? I'm going to multiply by 2, so that gives me 2 electrons here, and in order to multiply by 2, I need to put a 2 here in front, and I don't need to multiply this, so I can leave those as is. What did I do? You guys are giving me looks like.
Why did you do
H2SO4 instead of the M?
Because I just wanted to see if you guys were paying attention. Just wanted to see if you were paying attention. I was like, I did something wrong because your faces looked insane. I'm sorry. I don't know. Because it was right above it and I just wasn't paying attention. Yeah, mine too should be in front of nitrogens. Otherwise, that should make you make the crazy face. So, that okay? Now we're okay?
Yeah.
All right. So then the last step would be to balance your whole equation. And because there's a lot of stuff happening up there, I'm going to move this down. And you want to make sure everything else is balanced. So we know our sulfurs are taken care of. We know our nitrogens are taken care of. So next would be to look at our hydrogens. And it looks like those are balanced because I've got 2 there and 2 there. I have 2 oxygens plus 4 oxygens. So that gives me a total of 6 oxygens on this side. And I've got 4 oxygens on that one and then 2 oxygens there. So that gives me a total of 6 oxygens on that side. So now it's actually already balanced. I didn't have to add any additional numbers. And this is what you would write as your final answer. That actually wasn't that bad. Some of them are harder.
I'm trying to think about like, so like if you're talking about like if the nitrogen like on the product side is like there's like a different amount, what would you have to do?
Let's see if I can find it like that. I think we did the aluminum one in class. I felt like there was another one that had a weird balancing thing happening. Okay, so I'm gonna erase this. Is that okay? Are you guys stressing him out? That's weird.
Just left it go.
Okay, let it go. Okay. So aluminum plus MnO2 makes Al2O3 plus Mn. So in this reaction, Amir, we have 0 aluminums here, or is my oxidation state here, but over here it became +3. Okay, so, and then I would have what? +4 here. Does that have no charge on it? To 0? So in this instance, did we gain or we reduce? By 4 electrons. And then from here, did we oxidize? I guess I gain or reduce. Did we oxidize or reduce? Oxidize because we went from 0 to +3. So here we oxidized 3 electrons. Okay, so then in this problem, what we need to address is the fact that we want to make sure that our atoms are the same as far as the ones that are being oxidized or reduced. Manganese is. Aluminum is not. Okay, so each aluminum is going to lose 3 electrons. However, I had this reaction, I had to make 2 aluminums. So if I'm making 2 aluminums, then I know I had to actually have 2 aluminums to start my reaction. So I'm going to double because I just multiplied by what I had to do to make those equal. So really I'm dealing with 6 electrons transferring. And so now when I go to balance my electrons, I have to recognize that 6 electrons are being transferred. And that's the step there.
And that was because there's 2 aluminums on that side, but not 2 on this side.
Correct.
So when you had to balance it, then multiply it.
Correct.
So like in the steps, when we find it, we do like we balance the electrons, but then the next step is to balance the whole equation. So is that like if the electrons are about like
Okay, so you're going to balance the atoms 2 times. So you'll find your oxidation states, kind of figure out what's being oxidized or reduced, make sure you did it right. And then you'll balance those that are being oxidized and reduced as far as atoms go. Then you would balance electrons. And then you'll balance whatever atoms are left. So when you get to that very final step where I kind of rewrote mine, the only ones you really should be dealing with were things that weren't involved in oxidation and reduction.
Okay.
Does that make sense?
Yeah, that makes sense.
And so most of the time, that last step should be very few extra moves. Okay. Do you want to finish this?
Yeah.
Okay.
Because now there's uneven like electrons.
Right. And so what would be a good number to get these both to?
2 or 12.
Right. 12 to both of them. So we're going to multiply. I'm going to maybe write this. So I'm going to multiply this one by 2. Here's where it gets a little weird. If I need to multiply this by 2, that means I have to multiply how many I have by 2. So this was 2. When I multiply it by 2, it becomes 4. This was 1. When I multiply it by 2, it becomes 2. So I still have my 4 aluminums, excuse me. And remember, each aluminum is losing 3 electrons. So that makes sense that I got to 12 electrons. Did I lose you? That's a really hard, like, there's a lot of things to think about right there. Okay, and so then here, to get this to 12, I have to multiply by 3. So I'm going to go up and multiply my coefficients, which both happen to be 1, to turn both into 3. Just a little bit first.
So when we read it out, like and we're gonna balance the rest of the thing, we usually like not have to rebalance.
Will it usually?
When you make like the balance.
Yeah, I don't know if I would go as far as saying usually, but some of the times for sure.
That was fine.
Is this one already balanced? So we got 6
It is,
oxygens, 6
Yeah.
oxygens. So definitely check it. It's not a good idea to just assume that it is, but for sure, if you find it being that, don't get worried. Steph, did you have a question?
No, I got it.
Awesome. Kendall, did you have a question?
Oh, yeah. When, so after we got for aluminum, we added the 2 to the front to like make it equal with the aluminum on the side side. And then we multiplied it by 2. So when we're putting like it in front of the aluminum, are we gonna multiply, like if there were 3 in front of it, instead of the add 2 and multiply 2?
So you would always multiply. So like if this had been a 3 and I needed to double it, then it would have become a 6.
Okay.
That's a good question. So your other question, the other big question was about limiting reactants. What exactly do you want to know about limiting reactants? Like why iron was the limiting reactant?
Yeah, can you do that one?
Sure. I don't know that there's a lot for me to work out, but I can definitely talk about it. So the FRQ, and I can relate this really, the FRQ I liked that you guys did because it had to take some concepts we talked about for the silver lab and some concepts we talked about the redox lab and kind of put them together. And so remember in the silver lab, we talked about the fact that in your silver alloy, what had to be the limiting reactant? Why did silver have to be the limiting reactant? I don't- Right. So if our goal is to figure out, whoa, that's a weird way to write away, how much silver is in my alloy, and we don't react all of the silver, am I going to be able to get the right answer? No. So this has to be the limiting reactant because it's necessary for all of our silver to react in order to determine how much we have. So this is limiting because we need it all to react. So let's say I wanted to do a lab where I gave you, I think we did one that was like this in class. I gave you like a rock that had tin and copper in it. Okay. And so then we're going to do a redox titration, and we're going to react it with potassium dichromate. Okay. So between these two, which one would we want to be the limiting reactant? Which one? So you've got, what are we trying to find? Did I not tell you that? That would be helpful information. How much 10 you have in your reactant? Okay, so 10 is going to be your reactant. Well, but we were deciding between this number or this one. So whether you knew tin or copper, you know it has to be this one because we want all of what's in the rock to react. So when we're done with the reaction, what will we have extra of? This guy you'll have extra of. You have to have extra of this one because if we don't have extra, how are we going to know that we reacted all of this? There's no way to know, right? Even if they reacted in perfect amounts, it's really hard to tell that if you don't have extra here. These actually are conveniently colored, so when you can see when you get that extra color in there. Just like here when we did our silver lab, we had extra of our nitric acid. That was to ensure that all of the alloy dissolved. Then we also had extra of our sodium chloride to ensure that all of the Ag reacted with our chlorine. You're always going to add extra of the one that we're not like trying to measure. When you're trying to measure and analyze should be your limiting reactant always. Does that make sense? Yeah. So silver copper lab. So the HNO3 was excess. And then the NaCl was excess. And why did we use the NaCl in there? Okay, to bond with the Ag and the Cl. That's not enough information. As I was reading some of your post-lab questions, remember that we picked AgCl because
with silver, but not.
exactly. It'll precipitate with silver, but it won't precipitate with copper. And so I think that was loosely graded on your short answers. So you just want to be careful with that to make sure you understand that one. And then, so this would be conceptual between your limiting reactant. What if I gave you a solution of permanganate and I had you react it with hydrochloric acid and I wanted you to tell me how much manganese was in it? So you had permanganate solution, you dropped it into hydrochloric acid. Which one should you have more of at the end of the reaction? Which should still be there at the end of the reaction? Your acid. So that would make my limiting reactant. He's just kidding. Permanganate. So this is going to be my limiting reactant this one. Does that help? Is that where we were running into trouble with limiting reactants?
I was struggling with just the calculations. And if you gave us the amounts or whatever, and if you calculated them both out and you found the grams or whatever of each of the substances or the reactants, then how you could tell which one was limiting.
The one that makes the smaller amount is going to be the one that runs out first. If you're doing it like it sounds like what you were saying. So if you have 5 grams of H2 and 5 grams of O2, and they're trying to turn into water, so 2H2O, 2 2H2. So let's say that's my reaction. Okay, so you'd go from your grams, so 2 grams for every 1 mole, and then I have 2 moles of H2 for every 2 moles of H2O. It would be fine to stop at moles of H2O because down here you can get that to moles of H2O. Oops, it should be 32 grams of O2 to 1 mole, and then in the reaction it was 1 mole of O2 for every 2 moles of H2O. And so then you would solve out my 2 answers and get me to a final value. So this is going to be 5/2 versus 10/30. So you'd have to decide which one of those is going to be the bigger number. You guys do that? 10/30. So which one is the bigger number?
Oh, bigger than
5
Okay, so then this one can't be the right answer. So then my limiting answer would be this value. And so that would tell me that oxygen is my limiting reactant if I solved it that way.
Okay.
Does that make sense? That's what I think you were working through. Does that help? Okay. I just went to moles because we were trying to figure out what was limiting to practice that. You would have to read the question to kind of know what you're solving for. So now once you figured out the limiting reactant, I could just carry that out one more step and go from moles of H2O to 18 grams of H2O if you needed to know grams or whoever knows what you're solving.
So in this case, the oxygen's the limiting.
Yeah, this case, the oxygen's limiting reactant because it made the least amount. So what that means is that this one will have extra, this one will run out because you'll stop reacting once you make a third of your water. Okay, bye everybody.
Thank you.
Thank you.
You're so welcome.